So, as I promised in the previous lecture, today I will be talking about a very important device. This semiconductor physics is largely contained in this device. If you understand this device, which is called p-n junction, then it is very easy to understand many of the devices which are based on this basic unit of p-n junction. So, what is that? As the name indicates, you should have somewhere p-type doped semiconductor, you should have somewhere n-type doped semiconductor, and then they should meet to make a junction. But it is not that you take two semiconductors and join them to make a junction, one p-type and one n-type. You start with the same material, same wafer. If I talk in terms of silicon, the first thing is that you should have a very pure silicon material, and there are processes, well controlled processes by which you can grow very pure monocrystal silicon, and then they make some kind of cylindrical tubes or not tubes, discs, cylinders, solid cylinders, and then you can cut wafers of appropriate size. The impurity level has to be very slow if you want to make devices out of it, electronic devices out of it, and that impurity level must be, let us say, less than 1 part in 10 to the power 10. So, that is the starting material, and with this starting material, the first thing is this entire wafer is made either p-type or n-type, this whole thing. So, let us say we make it p-type. To make it p-type, you have to diffuse trivalent impurity like boron or something. So, it goes there. Here also you have very controlled processes. There are several processes by which you diffuse these impurities, and at the end you retain that silicon crystal. Silicon I am taking as our model semiconductor. In any kind of semiconductor you have to do all this processing, and so through very controlled processes without finally disturbing that crystal structure, you have to put these impurities at those lattice sites. So, this whole thing becomes p-type, and once this whole thing becomes p-type, after that you, in a very controlled fashion, you diffuse n-type, and for that some pentavalent impurities like arsenic or antimony. So, that is now diffused in a much more controlled manner, so that it goes only up to some depth. So, this side still remains p-type, but here dopants of pentavalent impurities are driven into this, they are diffused into this in a larger concentration. So, this side becomes n-type and this side remains p-type. So, you have p-type here, you have n-type here, and this is the junction. This is that junction. So, this is p-n junction, and if you want to use it for external world, you should have metallic contacts from where you can connect wires and put this into circuits. So, very controlled fashion, once again part of that metal is deposited, aluminum or some metal is deposited either on the back side or on the front side itself. You can have a P here and metallic contacts. So, for our discussion, I will be drawing this part of, let us say, this part of this system. So, I will write it, or this part of the system. So, I will show it in the diagram many times, maybe 20 times, a p-n junction as a rectangle like this, and then a line in between, and then one side is n side, one side is p side, like that. So, what I will be actually showing is this portion, this is n type, this is p type, here is the junction, here is the metallic contact, here is the metallic contact. So, this is I represent this as a metallic contact. You will assume that you have a metallic contact here, you have a metallic contact here. So, this is the situation. Now, if you do create this kind of a p-n junction, it is an absolutely unstable situation, because this is n type. What does it mean? It has huge number of electrons, large number of electrons, conduction electrons. Because of those pentavalent impurities, you have large number of electrons here, conduction electrons here, free electrons here, and you have some holes here. You have some holes here in between, small amount. Remember, N E into NH, that is fixed, Ni square. And for a ppm type doping, we had calculated that the number of holes reduces to few thousands per centimeter cube, but they are still there. And similarly, on this p side, this is p type semiconductor here. So, you have a large number of holes. You have large number of holes here, and then some electrons in between. There are some electrons in between. So, on the n side, you have majority carriers, that is E electrons, and minority carriers, that is H. On p side, you will have majority carriers, that will be H, and minority carrier, that will be E. Now, since this is that same crystal on which you have put these impurities, all kinds of movements are possible. Electrons can go from this atom to this atom to this atom to this atom to this atom. The holes can also go from here to here to here to here. So, all that usual electron movement and hole movements is allowed in this entire wafer, in this entire material, and therefore, having large concentration of electrons here and having a very small concentration of electrons here is a very non-equilibrium situation. If you have such a huge concentration gradient, and if the movement is allowed, they are allowed to go from here to here. Remember, the whole thing is one single crystal on which you have done all these diffusions, and therefore, that movement is allowed. So, if you have concentration gradient, you have large concentration of electrons here and very small concentration of electrons here, naturally there will be a systematic flow of electrons from the higher concentration side to the lower concentration side. It's a law of nature. You put your incense here in one corner of the room, and then this entire room gets that particular aroma, flavor, and that is because the concentration of those particles here is very large near that incense stick, and the concentration is low in other parts of the room, and then there is a flow from higher concentration side to lower concentration side. So, if this is the situation, you will have a systematic flow, we call it diffusion, systematic diffusion. Diffusion itself is some kind of systematic flow. So, of electrons in this picture, it will be from left to right, and of holes in this picture, it will be right to left. And keep track of what is happening in the actual crystal. This is the diagram on which we make, but if you think of actual silicon crystal, keep that also in mind, so that that physical connection is not lost. So, you have all those silicon, right, all those silicon atoms. Then at some places, if it is N type, you have put those impurities, and because of that you have those electrons, extra electrons which are in the conduction band, and they are going here to there to there to there. They are just going randomly, changing atom to atom, atom to atom, and so on. So, in the process they are going from this side to that side to this side, but since the concentration of electrons is large here, the number of electrons which are going in a given time from this side to that side, this side to that side, will be much larger than what can come from the other side, and hence there is a net flow. And similarly holes, if you have holes here, if you have large number of holes here, some holes can diffuse to this side. Hole diffusion, you remember, the bonded electron breaks from here, and then there was already a hole here, a broken bond was here. So, a new bond is broken here, and the electron, bonded electron, goes there, and the hole is filled here. So, this hole is gone from here and new hole is created here. We say that this hole has diffused. So, since large number of holes are there, once again the diffusion of holes from right to left in this figure will be much larger than the diffusion of holes from left to right, and hence what will happen? Hence you will have a charge density appearing. Remember, when you dope N type or P type impurities, the charge density does not change, it remains 0 in the entire thing, because whatever you dope is neutral. The wafer is neutral, the dope atoms that you are doping, they are also neutral. So, this entire charge density is 0, but now there is a systematic movement. Electrons going from left to right, what will they do? They will create a negative charge density here, and then these holes going from right to left, that will create a positive charge density here. Electrons leaving itself is creating positive charge density. So, both ways, holes coming from here, electrons going from here, both ways you will have positive charge density on this side and negative charge density on this side. So, you have a charge appearing rho which is positive, okay, rho which is positive here, and a charge appearing here, rho which is negative. So, in a N type or P type semiconductor, if you just have one semiconductor P type, you do not have charge density, but if you make this junction PN junction, then the charge density will appear. You will have positive charge density on one side, negative charge density on other side. But this thing does not extend up to the end. Close to junction this will happen, and away from the junction the situation is still neutral. So, this charge density appears only in a small portion which is close to junction. Why? That is because once the charge densities are there, you will also have an electric field. Okay? If the positive charge density is here, negative charge density is here, you will have an electric field like this. And this electric field will oppose diffusion. Okay? If the electrons are trying to come from left to right and the electric field is also in the same direction, the force on the electron is in opposite direction, negative charge, and therefore, that force will resist diffusion, will oppose diffusion. Similarly, holes coming from right to left, holes behave like positive charges. So, the force, well, you understand, holes behave like positive charges of certain mass, and therefore, we can still talk of force on the hole and all those things, but that force on the hole is in the direction of the electric field, that is towards right. Holes are trying to go towards left. So, this will be opposed by the electric field. And then there are some other processes I will be talking about. So, ultimately this charge density which appears here, all that happens close to this junction, say in a layer like this. Now, if the electrons are coming to this side and the holes are sitting here, these electrons will have a good probability of filling up these holes. So, the electron which has come, the charge carrier, the negative charge carrier electron which has come from left to right, finds so many holes there, and therefore, one or the other hole will definitely invite it, and it will accept that invitation gladly, and then it will go and fill that hole. What will happen? That electron, suppose this electron has gone from here and it meets this hole, it fills this hole. So, now there is no hole and there is no conduction electron, that pair is gone. Similar thing will happen everywhere. Holes which are coming to this side, they will also combine with the electron. What does that mean? Holes are coming from this side, that means a bond is broken from here and this hole comes and fills that, and then okay, hole is created here. So, it's this electron goes from here to here, this broken bond is filled by this electron, and therefore, this hole has gone from here, it has come to this side, and then this electron has filled that hole. So, that is also over. So, in that same fashion, you will have no charge carriers left. The electrons which are diffusing to the right, because of the large hole density there, they are trapped, and then if there are holes left, more electrons will come, and this width will be adjustable. So, as many holes are here, as those many electrons will go from this side and fill, and both ways, from this side to that side to that side. So, what you find is, yes, there are charge densities, but you do not have charge carrier density. Okay. So, that number of electrons per centimeter cube this, or number of holes per centimeter cube, this is 0, this becomes 0, this becomes 0. 0 means negligible, 1 or 2 here and there may still be there, but to be observable in a circuit. So, this is almost 0. So, in p-n junction, charge density appears in a region close to the junction. Right. So, close to the junction, there is a region in which charge density appears. On n side, you have positive charge density. So, this is 1, and then on n side, rho is positive, and on p side, rho is negative. And another interesting thing is, in this region, there are no charge carriers. So, the charge carrier density that is almost 0 for all practical purposes. Ne and NH, they become 0 only in this region, Okay. So, this particular region is known as depletion region. This is called depletion region. this is the region which is depleted of charge carriers. It does not have charge carriers, that is why it is known as depletion region. Now, what is the width of depletion region? How much will be this width? That depends on the concentration of the dopants. Okay. Remember, the dopants are there. This is N type up to here. From here to here, this is N type, and P type from here to here. So, although there are no charge carriers, this is still N type material. So, we have diffused those pentavalent impurities here. So, although the charge carriers are not there, the conduction electrons are not there, the holes are not there, but still those pentavalent impurities that we have put in, arsenic or phosphorus, they are still there, they are distributed in this entire region. This is still N type region. And similarly here, although there are no charge carriers, no holes, no electrons, but still it is P type. So, the width of this depletion region on the left of the junction and on right of the junction, that will depend on the concentration with which that dopants was put there, the impurity concentrations. All right. So, N type is we call it donor ions. So, ND, donor ion concentrations, the one we have doped. So, this is it, and this side is acceptor. So, this impurity is acceptor. So, this is the number of acceptors that we have doped per unit volume. So, that is here, and that decides this width. If it is large, if you have large concentration of impurities, then in a very small region, you have enough those electrons. Suppose this is large, Nd is large, then you have in a very small region, you have enough electrons which can go and neutralize that layer there. Similarly, Nd, Na and Nd, this they will decide. Larger this impurity doping, impurity concentration, smaller will be the width. So, if Na and Nd are not equal, you can have unequal width on the two sides of the junction. So, those are the things. Now, in this depletion region, you will have electric field, this electric field here, because you have charges, you have positive charges on this side, you have negative charges on this side, rho is positive here, rho is negative here. So, you will have electric field, and because of this electric field, the potential, electric potential will decrease as you go from left to right in this picture, right. You are going along the electric field. So, if you go along the electric field, potential decreases, E is minus dV dx. Okay. If I call this as x direction, then as you go, if the electric field is in x direction, then E minus dV dx. So, potential decreases. That means, this N side should be at a higher potential than the P side. We are not connecting any batteries. We have just put neutral impurities in a neutral semiconductor wafer. But we see that some electric field appears in this depletion region. In this region, there is no electric field because it is still neutral, no charge density, and here this is still neutral, no charge density, and effect of this will cancel out here. Okay, effect of this will cancel out here. So, you do not have any electric field here. So, potential is same from here to here, right. From here to here the potential is same, but then the potential starts decreasing, and here up to here it decreases, and then from here to here the potential remains same. So, if you think of these metallic contacts here and here, the potential here is larger than the potential here, because of this electric field, and you may think that okay, that's very nice, I have gotten a battery. I have a larger potential here, I have a lower potential here, so let me connect a bulb. And if this is a higher potential, this is a lower potential, this bulb should glow, the current should go, at least momentarily. But it doesn't happen like that. It doesn't happen like that, because here also you have different kinds of materials. You have the semiconductor, doped semiconductor here, and then you have the metal here. So once you go from a semiconductor to a metal, there is junction out here. So you do have a potential difference here also. As you have a potential difference across this junction, you also have a potential difference across this junction, and similarly across this junction. So here also semiconductor to metal, there will be a contact potential difference. Here there will be a contact potential difference, and here also there is a potential difference. And when you sum all these things, this potential finally it's same as this potential, this V1 and this V2. Contact, after the contact you have V1 equal to V2 after those metallic contacts, and so this bulb is not going to glow anymore. So in our next lecture, we will derive a relation between this potential difference that is created, which is also known as potential barrier. Why potential barrier? If you remove that or don't think of the metallic contact, we are still in the semiconductor, and then if I plot the potential as a function of x, how will it look like? This potential is higher and this potential is lower. So up to this depletion region, up to here, the potential is constant, and after that the potential will gradually decrease once you enter this depletion region because of this electric field. So it goes like this, and then again it will become constant, so it will be like this. So this is how the potential as a function of x will look like. This is that depletion region. Okay, well it's not, don't match. This is the potential, this is the depletion region. And if you think of electron, the energy of electron is q times v, negative of that. So if you plot another graph which is energy u of the electron, if you plot energy of the electron and then x here, and since it is negative, this whole thing will flip. Okay. So if electrons try to go from this negative side to that positive side, n type to p type, this side left to right, if they try to go here, and if they have some energy, say this is the energy of the electron, then it finds that okay, there is a barrier out here. There is a barrier out here. If the electron has this much of energy, then okay, then this electron can go into this region. But if the electron is having this much of energy, it cannot penetrate in this, at least classically. So this height, this difference is known as, or same as this difference. The units are different. This is voltage, this is energy. So this difference is known as potential barrier. It opposes the diffusion of electron from n type side to p type side. So in our next lecture, we will derive the relation between this potential barrier and other parameters of this p-n junction.